Greetings, my name is Dante Bolatti, and this video is an abbreviated version of the presentation titled Spacecraft Orbit Attitude Coupled Dynamics in Close Proximity to Small Bodies, that is part of my doctoral examination. This presentation will consist of three parts. I'm going to start with an introduction covering the problem statement and contributions of this research. Then the second section has three subsections, each one corresponding to a part in the dissertation, being the first one about modeling orbit attitude coupled dynamics, the second one about attitude actuation, and the third one about accurate propagation and model parameters estimation. Then I'm going to finish this presentation by presenting some concluding remarks and future work. So in recent years there has been an increased interest in asteroid exploration missions, mainly due to scientific purposes, mining and fuel extraction, and planetary defense. There are several challenges presented for close proximity operations, mainly due to the highly irregular and weak gravitational field that these small bodies present. Additional perturbations such as orbit attitude coupling and solar radiation pressure add to the challenges for close proximity operations. So the main goal of this research is to develop high-definition models and techniques that allow us to improve the analysis and control of spacecraft dynamics in close proximity to small bodies, including long-term behavior and model parameter determination. An accurate dynamics model of the spacecraft motion helps us to improve the efficiency in the spacecraft control system, therefore allowing to exploit the natural dynamics around the small body. This will consequently lead to a reduction of propellant consumption, extension of mission time, and an increase in the accuracy of the asteroid characterization. In this research, there are four main contributions, being the first one the introduction of a novel high-resolution gravity field model for asteroids that captures the orbit attitude coupling, the second one the analytical computation of the full set of allowed values for the second-order coupling force term due to all possible spacecraft orientations, considering a point mass primary. The third one, the introduction of translational geometric integrators of higher order for propagation of coupled dynamics about asteroids, including non-conservative forces. And the last one, the development of an estimation method for computing non-homogeneous mass distribution using a core and mantle approach for modeling the asteroid. With these comments, let's go now to the first topic of the research, modeling the orbit attitude coupling phenomena. First, a quick discussion on the background will take place. This format will be repeated for the two other parts. For close proximity operations, several models that represent the gravity field exist in the literature. Among these, the three most used are the ellipsoid model, the point masses or mass cone model for mass concentrations, and the polyhedron model. As we can see, the ellipsoid model doesn't accurately capture the shape of the highly irregular asteroids. The point masses model does capture the irregularities, however, it has a low resolution near the surface due to the separation between point masses. The most accurate model in the literature is the polyhedron model, that is analytically exact for a constant density polyhedron. All these models consider the spacecraft to be a point mass. When the spacecraft gets close to the asteroid, its size can become comparable to that one of the small body and can no longer considered to be a point mass. It should be considered to be a rigid body. Therefore, there is a coupling between the translational and rotational motion that can be quantified by the parameter epsilon. Several models in the literature that capture the orbit attitude coupling exist. The spherical harmonics model is one of those. However, it presents several convergence issues in close proximity to the asteroid surface. The next model is the point masses considering a rigid body spacecraft. This model is more accurate than the spherical harmonics. However, as mentioned before, it presents a low accuracy near the surface due to the separation of the mass cones. The most accurate model right now in the literature is the polyhedron expanded up to second order that accurately captures the orbit attitude coupling phenomena for rigid body spacecraft. However, it is very slow and not computationally efficient, so it cannot be used in real-time control applications. For computationally fast calculation of the gravity force, the mass cone model is the fastest one. Then, for a single point mass, the gravitational force can be expanded to higher order terms, accounting for the shape of the rigid body spacecraft, as shown here on equation 1, where we see that the coupling is done through the J terms, the inertia terms, in the second order force term. Considering now a point mass spacecraft, the gravitational force due to multiple mass cones can be computed as shown in equation number 2, being this the fastest method from a computational point of view. Now, for a rigid body spacecraft and for an asteroid field with n-point masses, the gravitational force can be computed as shown on equation number 3, where the first term represents the 0th order force, considering the spacecraft to be a point mass, and the second term represents the higher order force considering the rigid body spacecraft. This is considering the coupling effects. So in order to increase the resolution of this model, we replace the first term by the polyhedron force, effectively capturing the highly regular shape of the asteroid with high definition and keeping the coupling terms due to the multiple point masses inside the asteroid shape. Then, for computing the equations of motion, a set of reference frames and a model for the asteroid and spacecraft should be defined. This is done here on the left side of the screen, where we see that we have several frames, one fixed on the Sun, another one fixed on the asteroid, another one fixed on the spacecraft, and multiple reference frames inside the asteroid that have one of their axes pointing towards the spacecraft. We consider the asteroids to be constant density polyhedrons for now, and we consider them to be point masses for their translational motion about the Sun. Additionally, we consider that all asteroids rotate with constant angular velocity about their largest moment of inertia axis. With these considerations, we can now write the equations of motion for the rigid body spacecraft, as shown here in equations 6 and 7. For the translational motion, the gravitational effects of the Sun are considered, and coupling terms up to the fourth order are retained for certain cases, as shown in both equation 6 and 7. The rotational dynamics follow the classic form of Euler's equation, as shown here in equation 7. With these equations of motion, a comparison between the proposed model and two models found in the literature is performed for validation. For this, trajectory and attitude are propagated using the proposed model, and the results are compared against an exact model. Another accurate model is included in comparison in red. The error in trajectory is very low when compared to a more accurate model. However, this is not the case for the attitude error. Nevertheless, this doesn't have a large impact, since in real applications the spacecraft is oriented specifically in a direction, and the gravity gradient torque is treated as a perturbance that is compensated. Having developed a model that captures the orbit attitude coupling, let's see now how the coupling effects can be used for control. As previously mentioned, the magnitude of the orbit attitude coupling can be measured by the parameter epsilon. The effects of the orbit on the attitude of the spacecraft have been well studied in the literature through the gravity gradient torque approach. However, this is not the case for the effects of the attitude on the orbital trajectory of the spacecraft. If properly quantified, these coupling effects can be used as an actuator or a supplementary control force. So due to the coupling effect, pointing the spacecraft in a certain direction can have beneficial or detrimental effects. So the question is, how can we exploit the beneficial effects? Several numerical methods in the literature used to estimate the attitude for the desired coupled force orientation exist. However, these are numerical in nature and not very efficient. So we see that there is a need to have an analytical approach to obtain the set of allowable coupled forces due to the attitude of the spacecraft. For the analysis that follows, only the second-order force terms are considered to make the problem mathematically tractable. The solutions can be then generalized numerically for multiple point masses. In order to analytically quantify the effects of the attitude on this translational force, first we resolve this force in the FP frame that has its x-axis pointing toward the spacecraft, as shown before on slide number 7. This returns the form of the second-order coupled force shown in equation 10. The goal then is to find the boundaries of the regions where this force term evolves for all attitudes of the spacecraft. For this, a single point mass is placed at the center of the asteroid. The results obtained show that the boundaries are 3 ellipsoids of revolution, 2 lying inside the larger one. Here, the center, semi-major and semi-minor axes are shown for the first ellipsoid, and the other 2 have a similar form. Consider now a traditional spacecraft. There are 3 solutions along the XP axis, corresponding to each axis of the spacecraft body fixed frame, pointing towards the point mass, as shown on the following video. Here, it can be seen that the orientation that maximizes the force in the XP axis, or radial direction, is the one that has the spacecraft pointing its Z axis towards the point mass, while the minimizing one is the one with the y-axis pointing towards the mass cone. These results indicate that the possibility of using the attitude as an actuator exists by changing the magnitude and orientation of the second-order coupled force by orienting the spacecraft in specific directions. Next, based on these results, the coupling effects on equilibrium points near asteroids will be studied. Considering our rotating frame of reference, we can define a generalized effective potential that includes both the gravitational potential and the effects of centrifugal force, as shown here in equation 11. In this equation, the coupling effects are introduced on the term u, and by computing the gradient of this generalized potential term and making it 0, the position of the equilibrium points can be obtained as shown here in equation 12, where the attitude-dependent force term has been made explicit. Considering now a large spacecraft above asteroid Bennu, the equilibrium point positions are affected by how the spacecraft is oriented. This is clear by looking at the positions of points E3 and E4 and E7 and E8 that change locations depending on the spacecraft attitude. This change in location indicates the possibility of controlling the spacecraft using attitude actuation. If the system using this type of actuation is controllable, certain configurations can be more controllable than others. Let's see now how can this be measured. In order to compare the controllability of different system configurations using attitude actuation, first the system needs to be linearized about the equilibrium. We do this by performing a state space realization of the system, as shown here in equation 13, and then computing the controllability gradient by solving the Lyapunov equations shown here as equation 14. Then we can perform an eigenvalue decomposition of this controllability gradient, and the eigenvector corresponding to the largest eigenvalue indicates the most controllable direction in state space. So this means that the controllability gradient provides the degree of controllability of the system. The way that we can compare how much more controllable a system configuration is with respect to another one is to measure this degree of controllability. For this, a cost function is defined as shown here on equation 16. This function represents the minimum energy required to transfer the system from the initial state to the final state. In this case, the controllability gradient is formed by stable and unstable parts, and the transformation of the state variables is performed in order to arrange the A matrix in a special form. Using this cost, it was found that for asteroid Bennu, the most controllable system configuration is the one where the spacecraft is located at the equilibrium point E4 with an orientation that maximizes the in-plane coupled force. Due to the low magnitude of the coupled force, its effect is more visible by looking at the long-term evolution of the system. This takes us to the last part of this research, where a fast numerical propagation method will be developed to this end. Traditional numerical propagators in the literature directly integrate the equations of motion, and they do not maintain conserved quantities. So this means that any error in one aspect of the dynamics gets translated to the other one through the orbit-attitude coupling effect. Additionally, they require several computations of the acceleration of the spacecraft at each integration step, making them very slow. For these reasons, in recent years there has been an increased interest in geometric numerical integrators, of which the Galerkin variational propagators are the most promising. This is because they allow the construction of higher order methods, they are very stable and accurate for long-term periods, and they preserve the structure of the system, being computationally fast at the same time. The geometric methods developed here based on the Galerkin approach allow us to propagate translational dynamics for long time periods, thus allowing us to better analyze the effects of the non-homogeneous mass distribution. For this, first a model for non-homogeneous density inside the asteroid should be implemented. Here the core and mantle model is considered, where we assume that the core is a reduced version of the shape model of the asteroid and it's more dense than the surrounding mantle. If we can estimate the mass density distribution in the asteroid, the model is fully characterized. For this, several methods exist. In the literature, the classic estimation is done via the spherical harmonics model, but as previously mentioned, it presents several convergence issues in close proximity to the asteroid surface, and additionally there is a loss of resolution for highly irregularly shaped asteroids. There are other alternatives, of which we are going to use the MassCon one for estimation in this research. Given the coupled model, then, if the coupled force can be measured, can this provide more information to make the estimation process more accurate? In the next few slides we're going to examine this question, but first the Galerkin numerical methods will be developed. The Galerkin variational integrators can be constructed by approximating the discrete Lagrangian using high-resolution methods, as shown here on equation 16. The better we can approximate this Lagrangian, the more accurate the integration method becomes. For higher accuracy, the Galerkin methods use polynomials for approximating the trajectories and a quadrature rule for approximating the action integral, as shown by the white curve on the figure that approximates the trajectory in green. This white curve is known as the Galerkin curve, and its analytical expression is given by equation 18. We can then use this equation to form the Galerkin general method, shown here as equation 17, where we can see that the first three equations need to be solved implicitly in order to propagate position, and the last equation can be used to propagate momentum. Non-conservative forces can be included in the Galerkin methods by discretizing the mass potentials and incorporating them into the gradient of the gravitational potential in equation 17. To see how these methods behave, in the next slide a comparison will be performed against classical methods found in the literature. The position and normalized energy errors are shown in the left side of the screen for the propagation performed about Cleopatra for 150 days, using a large time step. It can be seen that the position error for the three Galerkin methods is very low when compared to the traditional methods in the literature. The energy error shows that the non-geometric methods artificially generate or dissipate energy. However, energy conservation is not an indication of the method's accuracy, as shown here by the second-order variational integrator in orange. We see that this method maintains the energy throughout the simulation, however, it's very poor for propagating trajectories for long-term periods. We can also see that the discretization of the non-conservative forces is very good, and the accuracy of all three Galerkin methods developed is excellent when compared to other methods, especially using long time steps. Now, being able to perform accurate long-term propagations, let's see how the non-homogeneous mass distribution can be estimated using the coupled dynamics. First, an accurate model of the non-homogeneous density inside an asteroid is defined using a core and mantle approach, with mass cons to account for the coupling. The asteroid mass can then be computed as the sum of a term for the core and a term for the mantle, and the same applies to the propagation force model. This model is used to generate the measurements, simulating a real mission scenario. For estimating the model parameters, there are three unknowns that require estimation: the core ratio and the mass-con masses. The mass-con masses for the core and mantle can be estimated by solving a non-negative linear least squares problem, as shown here in equation 21. Then, for the core ratio estimation, an optimization problem is solved by looking at the residuals after the fitting is performed via equation 21. Also, during this process, the measurement model is different from the propagation model, so it is computationally faster. Finally, we see that the measurement matrix is dependent on both the attitude and position of the spacecraft, so this information should be available as well. Results for the estimation problem show that incorporating the coupled terms increase the accuracy of the estimation. This is clear by looking at the core and mass estimation plots shown in the left side, where using the full model with coupling produces more accurate results than using the model without coupling. This estimation process presents large errors independently of which method is used. This is due to the ill-conditioned nature of the mass-con estimation problem. Finally, propagations performed with the parameters estimated using both the coupled and uncoupled model are shown on the right side of the screen, where we can see that the propagations performed with the parameters estimated using the coupled model, this is the full model, are more accurate than the one using the parameters estimated using the uncoupled model. This analysis allows us to obtain the model parameters and thus concludes the main body of the research. Next, we'll cover the conclusions and future work. During the development of this research, a novel gravitational field model was proposed that is accurate, computationally fast, and that it can be tuned. It also captures the orbit attitude coupling. Additionally, the analytical quantification of the coupled force was done for a single point mass, and we saw that we can control the coupled force via the attitude of the spacecraft. Then, geometric numerical propagation methods were presented based on the Galerkin approach. We saw that they are very accurate and very fast for long time steps and very long integration terms, and they also can include the non-conservative forces. And then finally, we saw the non-homogeneous mass estimation problem using a core and mantle model for the asteroid, and we noticed that the accuracy of the estimation problem is improved by considering the coupled forces. Several items are left for future work, such as 1. Improve the mass-con distribution inside the asteroid, 2. To perform orbital control via attitude actuation, 3. To use a combination of the solar radiation pressure and gravity coupling for control, 4. To expand the Galerkin methods to include rotational dynamics of the spacecraft, and 5. The extension of the analysis performed here to binary systems, where in this case the secondary asteroid is comparable in size to the primary asteroid and they orbit in very close proximity to each other. This concludes the presentation. For more information, please feel free to contact me via the email address shown on the screen. Thank you for watching this narrated version of the presentation.